Aliens, extraterrestrials, celestial beings. Call them what you will. We spent a lot of time here on Earth preparing for contact with some sort of intergalactic creature. Perhaps a nice one like E.T.
He's a man from outer space, and we're taking him to a spaceship.
Or perhaps a bad encounter, as in War of the Worlds.
What's that? There's a jet of flame springing from the mirror and it leaps right at the advancing men. It strikes them head on. Lord, they're turning into flames.
There's no shortage of artistic interpretations of aliens, but far, far away from the bright lights of Hollywood, a lot of questions remain, such as, what might extraterrestrial life actually look like? What would we have in common? Would we recognize some piece of ourselves in them? And what would actually be alien to us, Earthlings, accustomed to carbon-based, water-loving life? And cards on the table, how likely are we really to make contact? Odds are, Earth probably doesn't host the only life in the universe. But if we ever do find it, it'll probably look like, well, why don't we find out? Today on Nova Now Universe Revealed, the search for alien life in our galaxy. For anyone or anything listening out there. I'm your friendly podcast hosting Earthling, Alok Patel.
When you think about the word for alien, we think about extraterrestrial. So, okay, we got to find a terrestrial world. But in Chinese, right, I'm half Chinese, the word for alien in Chinese is Weixingren, which is other star person. So I think in Chinese, they're already ready for us to find life on an exoplanet because we got to go to another star, which is pretty cool.
Anjali Tripathi is an astrophysicist at NASA's Jet Propulsion Laboratory and the science ambassador for NASA's Exoplanet Exploration Program. In other words, she searches the galaxy to discover exoplanets, that is, planets outside of our solar system.
I tell people my job is sort of like being Where's Waldo, but on an astronomical scale.
In the last few decades, astronomers have discovered thousands of exoplanets revolving around stars in our galaxy.
So it's amazing to me that within my lifetime, we've discovered all of these exoplanets. Because I remember being a kid, there were 9 planets, and then we lost one, poor Pluto, and then the number just kept growing.
Though there's some dispute over when the first exoplanet was found, there were definitely some important discoveries made in the 1990s.
In 1992, there were these Polish astronomers who were looking at millisecond pulsars. They've got these beams of light coming out of them that they're spinning really fast. So that's that millisecond thing that each second is going around like 100 times.
To understand the pulsar timing method, picture a lighthouse with its light beam revolving at regularly timed intervals. Scientists can measure the timing of pulsars, so if they detect that the rotating light beam is a little early or a little late, that could be due to a planet's gravitational pull, suggesting there might be a planet orbiting that neutron star.
And so it was from observing these pulsars and noticing the timing was off that these astronomers discovered that there were a couple of planets actually orbiting these dead, dying stars. But in exoplanet astronomy, we often also talk about 1995 as being this big turning point, because that's when we started finding planets that were big, puffy, Jupiter-like planets, and they were actually found around stars that are like our own sun. So rather than a dying star, these are solar-type stars. And so that was the sort of beginning of the era of exoplanet astronomy.
Could you walk us through the methods that are used to discover these exoplanets and how do they work?
So the way that 51 Pegasi b in 1995 was discovered, that first planet was discovered using what's known as the radial velocity or Doppler method. And that's the fact that a planet and its star that it's circling, or stars, are in a little bit of a dance, kind of like you could imagine that star is wearing a hula hoop. And in order to keep that hula hoop going, you've got to wiggle your hips. And so that star is going to move back and forth. And that's actually something that we can track the motion of that star's light here on Earth.
So as a planet travels around a star, making it wobble back and forth, the wavelengths of the starlight get alternately squeezed and stretched as the star moves slightly closer or farther from us, respectively.
Similarly, if you've got just the right angle that you're looking at the star and planet, you can actually see the planet or planets crossing in front of the starlight, blocking it out a little bit. So you've got your starlight blinking at you, dimming the light repeatedly. And if we can see that happening regularly enough, we say, hey, there might be a planet. And so that's a really popular method called the transit method. There are other methods that we're using to find planets, but they haven't yet found as many, in large part due to technology limitations.
So far, we've found a majority of the exoplanets using the transit and the radial velocity methods. But in the future, scientists hope to capture direct images of exoplanets. Say cheese, you sexy exoplanet.
So this is where you actually see the planet, which is the thing that you most want to see because you're finding it directly. But you actually can't do this in a lot of cases right now because it's like trying to look at, a fly next to a lamppost, right? The light is so blinding, it's really hard to see unless that's really far away from the star. But with the coming technologies and upgrades in instrumentation, we're really hoping that we can then be able to block out the starlight and see planets close in so that you can find these worlds that are just as exciting as with the other techniques, but we can see the planet.
Astronomers have been able to detect exoplanets from here on Earth, but the number of known exoplanets exploded when NASA launched its Kepler spacecraft in 2009.
3, 2, engine start. 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
It would not be an overstatement to say it revolutionized the field of exoplanets because just staring at this one patch of the sky, it found thousands of exoplanets. And when it found so many exoplanets, right, we were in the tens, hundreds of exoplanets before Kepler. Not only did it find a huge number, but it found an incredible diversity or menagerie of planets because we found planets of all different sizes. We found that they had all kinds of different properties from anything that we had seen thus far. And so Kepler really opened our eyes to what else could be out there that we just are starting to scratch the surface of.
The Kepler Space Telescope relied on the transit method to find exoplanets. Since 2018, it's been remaining in quiet orbit around the sun, far from Earth, enjoying its happy retirement. So that's Kepler. Can you tell us about TESS, the Transiting Exoplanet Survey Satellite Mission?
TESS is the follow-up, or TESS is the successor to Kepler. It is still operating at this very moment. Unlike Kepler, which stared at one little patch of the sky, TESS is actually looking at 85% of the sky. So it's looking at the whole sky. And what it's doing is saying, hey, let me try and find the nearest, brightest candidates where we can then go and follow it up for planets. Because kind of like you might see someone in a crowded room, who's got pink hair, and you say, oh, they seem kind of interesting. But if you're far away, you're never going to be able to get to know them.
Scientists are using TESS to locate nearby exoplanet candidates to observe with the James Webb Space Telescope, which launches next month in December 2021. This powerful telescope will zoom in on these exoplanets, observing their infrared light and analyzing their atmospheres. So far, scientists have confirmed the existence of over 4,500 exoplanets in the Milky Way, and that number continues to grow. We've only scratched the surface of the total number of exoplanets in our galaxy alone.
There are about 100 billion stars in the Milky Way galaxy. Milky Way is one of maybe 100 billion galaxies. And we know that every star, almost every star, we should say, has a planet or probably a few. So that means that within the Milky Way, we've got hundreds of billions of potential planets to go out to discover. So you think about that number and the fact that we've found a few thousand. There's this huge room for discovery, and it's hard to say at what point we'll catch up with the total number of exoplanets, but I'd say there's going to be a lot more coming.
When we think about planets orbiting stars, it's natural to imagine our own solar system and how it's configured, with rocky planets closer to the star and gaseous planets farther out. But that's not always the case.
So one of the really common populations of exoplanets that we find, and I'm very fond of them, are called hot Jupiters. So these are big, planets that are the size of Jupiter, really puffy gas giants, but they're about 100 times closer to their star than Jupiter is. And so that means that you put this ball of gas right next to the star, and it's kind of like blowing a fan at somebody with a toupee. You're going to watch things sort of blow in the wind, and it's going to reveal some things. And so the reason that we find so many hot Jupiters, it's, as you might imagine, easier to see big effects and big things in space than little ones with our technology. And if it's right next to the star, that means it repeats a lot faster. So a year could just be about 4 days for some of these planets. And so that means that, you only have to watch it for about 12 days to say, oh, hey, that might be a planet. So with these exoplanet systems, we not only find that the planets within them can be really diverse and have different sizes and temperatures and distances from the planets in our own solar system, but also you find that they could orbit multiple stars. You could have the alignment be totally different. You could be orbiting the pole of the star, so you might have seasons every couple of hours on your planet. And so just because we haven't found a copycat of the solar system, I think what we're finding is that doesn't mean that we are the only ones who look like this. It's just that that's the only thing that we've seen yet, and there's a lot more to come.
Once astronomers discover an exoplanet, they use what they know about its physical properties to picture what it might look like on its surface, if it even has a surface.
So you can imagine there are planets that are just so close to their star, or, the star has just got all these properties that make it really hot on the surface of a planet. And it can be so hot that you wouldn't even be able to have rock sit there without melting. You might be seeing a world of magma, or we like to call them lava worlds, which of course is totally foreign to us here in the solar system. But we find lots of planets that have those properties. I can take the mass divided by the volume of a sphere and say I have a density, and I can compare that to the density of things I know. So if that density is really light, I might say, hey, that's a gas giant planet. We can also say, I've got this density that's kind of in between rock and gas. There must be a good fraction of water on that planet. Maybe that's an ocean world or a water world. It can be so hot on some planets that the clouds have the ability to effectively rain glitter, or some of the minerals that are used to form rubies and sapphires. And there are some planets also, if we go back to our pulsar planets, where you've got that light beam spinning all the time. If you were on that planet, it would probably feel like being at a disco all the time, right? Because you've just got the strobe light in the sky going around. So between that and the fact that you've got planets that can orbit multiple star systems, so Tatooine is not just from the movies. We've found planets that are orbiting 2 stars. We've found planets orbiting 4 stars, a whole number of things. It's not one day, one sunset. It's lots of sunsets to get to enjoy. There's all kinds of things that I can't even begin to tell you how excited I would be if I got to see that, because right now it's just all in our imagination based on the data.
And learning about these alien worlds can actually teach us something about our own little blue planet.
So it turns out that some of our atmosphere actually drifts off into space on its own, right? It gets enough energy that it says, hey, I can overcome gravity. I'm out of here. And it's something that's pretty mild on Earth. But when you look at hot Jupiters, you end up having just huge amounts of gas, right? We're talking millions of kilos and just drifting off into space. So the fact that I now know, hey, the Earth, Mars, even Pluto, they've all got their atmospheres escaping off into space, is something that you had to see it on a really extreme scale in exoplanets to appreciate within our solar system. And so being able to see the diversity of what's out there, and as we're exploring and finding more worlds, it makes you really reflect back on how special it is that here we are. And so I often get the question, what's your favorite planet? And people think it's a cop-out, but my answer is always Earth, because this is the one that I get to experience and enjoy. And I think it's really special to see how unique that is for now, until we find more that's out there.
With so many exoplanets in our galaxy, you gotta wonder, could any of these alien worlds be home to actual aliens? The search for life on other planets after the break.
My parents were showing me a partial eclipse of the sun when I was 12, and it blew my mind that anyone could predict the movement of the skies like that. And it just felt like the greatest, it still does feel like the greatest power imaginable. And I wanted it, and so that was it.
Clara Souza Silva is an astrochemist at the Harvard-Smithsonian Center for Astrophysics. Her job is to search the galaxy for indications of alien life.
And in my specific work, so looking for signs of life at a molecular level, I'm looking at things that are so small, so far away, that we're talking about molecules on atmospheres surrounding planets, orbiting stars, many, many, many light years away. And to do that, you need to understand molecular behavior, which means understanding quantum, how the quantum behavior of molecules produced by alien life can be detected from here. So now I'm a quantum astrochemist.
This is so cool. This is like one of the coolest realizations of a childhood interest. As a quantum astrochemist, Clara examines the atmospheres of faraway exoplanets to look for chemical signatures of life. But life can take many forms. So how does someone like Clara define the term life in her otherworldly searches?
So it is inevitable that we are biased. I'm human, I use oxygen, and most of the life that I like also loves oxygen. And so one of the things we end up looking for a lot is Earth-sized planets with thick atmospheres that are oxygen-rich. But it's worth remembering that life is not one thing. For example, on Earth, for the longest time, there was no oxygen in our atmosphere, and life thrived. We then did fill the atmosphere with oxygen, and that was actually a biological catastrophe. Everything died. Very little survived that transition. It was an absolute global massacre that we're very thankful for, because out of that came life that eventually evolved into us. But that is one of the things that in my work I think about a lot, that Earth has been many planets. Life, no matter how different and weird it might be, it will still have to be on a planet or on a moon, surrounded by some environment, and it will have to make use of that environment. And when it does, it will take the stuff from its atmosphere and its surface and its liquids, and will do things with it, and then it will produce waste products, because nothing in the universe is so perfect, so efficient, that it doesn't release something, doesn't produce waste. And I look for that waste.
So I want to circle over to some of the molecular chemistry, biology that you were referring to. I remember learning about the acronym SPONGE and how every life form we know contains these elements: sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen.
Very good.
And is it just these chemicals that we know of that are necessary for life to exist? Is there more that you're looking for? Could you tell us a little bit about your search using these elements as a guide? And is it possible, is there non-carbon life forms out there? Are there aliens who look at us and they're like, who are these weirdos using carbon?
So sponge or schnapps, depending on usually which side of the Atlantic you are not the only elements needed to make life. They're just most popular ones. They're just available. And so it's true that when I do my work, particularly when it's really computationally demanding, I start with sponge, schnapps. I start with the obvious elements. And so, yes, these are popular, and they're popular for a reason. They're really good at variety. You get a lot of biochemical variety from these elements. A lot of interesting evolutionary choices can be made with these environments. With water as a solvent, it's a rich playground for life. And so we do start there, but I certainly don't stop there. Life uses other, more obscure elements. Currently, in my database of biosignatures that I develop, I consider 16,367 different molecules.
Whoa.
All of which I think could be associated with life and detectable on alien planets. So that's a lot of potential signs of life. So I definitely try to not create too strict a boundary on my expectations of life.
A biosignature is any characteristic that can be considered an indicator of life. Clara's research focuses on molecular biosignatures in the atmospheres of planets, but not every exoplanet is included in her searches.
For example, I put boundaries when I look where if it's so high pressure and so hot that complex molecules would just disintegrate, I'm calling that a no-go. So there are limits here. A planet that has no atmosphere and no safe subterranean environment, like an underwater liquid ocean, is also not good. A planet that is so close to its star that it gets destroyed by stellar winds and radiation at regular intervals, that's probably not good either. But outside those limits, there's a huge variety of planets and stars that they orbit, and we look for anything weird. So no, we're not just looking for life on Earth-like planets. We're looking for life on moons of planets. We're looking for life on planets where we know very well we would die a quick and horrible death. So we very much look at anywhere that could be considered habitable by some definition.
If an exoplanet is determined to be a good candidate for hosting life, astrochemists like Clara analyze the molecules in that planet's atmosphere to look for biosignatures.
Molecules interact with light, and that is a universal truth. We can experience it here, and we can watch it happen everywhere else in the universe. And so when we get light from a star, we can break up that light into a rainbow. We have basically fancy prisms that break up the light from stars. And when we do that, we get a star's rainbow. And if a planet with an atmosphere containing molecules crosses in front of that star, we might not see that event because the planet is so small compared to the star and they're both so far away. But the light from that star can go through the atmosphere of that planet. And when it does, molecules in that atmosphere will absorb some of the colors of the rainbow. And so we see this beautiful stellar rainbow once every orbit change, and some colors go missing. And we know from work here on Earth that, for example, if light goes through an atmosphere that contains water, then there's very specific colors of the rainbow that water will absorb. Very different from if that light goes through an atmosphere that has methane, or phosphine, or ammonia, or molecular oxygen. And so basically, we see what colors are missing from this rainbow, and we know what molecules that light must have gone through.
Clara has a favorite molecule to search for in the atmosphere of exoplanets, phosphine.
Phosphine became very much my favorite molecule, in that nothing I will ever love will produce phosphine. Phosphine is an extremely dangerous molecule for the life we find pleasant. But not all life will like oxygen. And there is still on Earth environments and life in those environments that doesn't really like oxygen. These are anaerobic life forms in swamps and in our intestines and at the bottom of lakes. And this life is trying to avoid oxygen as much as possible. And that life produces phosphine. So when I figured that out, I thought, what if a whole planet was like that? We as a planet used to not be filled with oxygen. Most planets we have found are not filled with oxygen. So maybe life there could produce phosphine. And so we often look for these molecules on these alien planets. But the question becomes, if you find these molecules, have you found life? Or could there be some strange geological event or thunder and lightning falling on some type of liquid that could produce these molecules without any life being needed? We call these false positives for life. And most molecules have them. Most molecules that life makes are not that hard to make. And so the universe makes them accidentally, spontaneously, with no need for life. And how do we tell the difference? And that's what makes phosphine so special to me, because phosphine is almost never made spontaneously. So it will be hard to find it. But if we do, it will very likely mean life, because it is so difficult to make. And that just seemed extremely cool.
Scientists aren't just scanning faraway exoplanets. There are other planets in our own solar system that might host alien life. And since phosphine could be an indicator of life, it was all the more interesting when Clara and her team found phosphine in the clouds of Venus in September 2020. But the data are still under debate.
This is done very much at the edge of technology with sensitive, noisy data that we're still arguing about. There are ways of processing the data where the signal disappears altogether. And there's ways of processing the data where the signal is there, loud and clear and statistically significant. And even teams that agree that the signal is real disagree on whether it must be phosphine. There are other molecules whose quantum behavior can mimic that of phosphine in some circumstances, like sulfur dioxide.
Ultimately, we need to collect more data to know for sure.
And if we do, it will be wonderful, not just because it means we have neighbors, but because we have neighbors producing phosphine, my favorite sign of life.
Gazing at distant alien rainbows isn't the only method we've used to search for alien life. The SETI Institute, short for Search for Extraterrestrial Intelligence, has been looking for evidence of technological civilizations in our galaxy since 1985. But so far, we haven't had any luck with extraterrestrial communications, no matter what Hollywood says.
We have a ships in the night problem. We have had, let's say, a couple of centuries of communication and less than that of listening in. It is possible that we as a civilization will obliterate ourselves in only a few centuries more. On Earth, we've had, I think, historically something like 5 billion species and only one intelligent, and barely so, and for very little time. And so it becomes very easy to imagine a galaxy full with life, teeming with life everywhere, but very few civilizations able to communicate for long enough before they're obliterated.
What exactly are technosignatures, and how do we actually search for them on other planets or try to detect them?
So complex pollutants are a very depressing but very reliable signal for life.
So if aliens were looking at Earth and detected the pollution we have way too much of in our atmosphere, they'd be like, oh, there's probably life there.
But they would be sure that they got really lucky and caught us just before we completely destroyed the environment and ourselves. So looking for complex pollutants, I would love to find them because there would be no ambiguity, but I would be very worried for my alien colleagues and their longevity.
So do you think this will humble humanity if we do find life? Like what difference do you think it'll make in every person's mind?
I certainly hope so. I think a little humility would go a long way. I think people sometimes talk about how it will unify us because now we have this, common enemy, and I certainly hope that does not happen. That we don't just transfer our desires for us and them to a galactic scale. But I certainly hope that it will feel humbling and comforting all at once. That's how it feels to me. But that's why we need more than quantum astrochemists and engineers. We definitely need philosophers and lawyers and poets and artists to make sense of it all.
And odds are, of the hundreds of billions of possible planets in our Milky Way galaxy, some number of them are likely to host life.
So my favorite way of thinking about this is, are we special or are we not? And the sun is a wonderful star. I love it. Wouldn't trade it for the world, but is not a particularly special star. The molecular cloud that formed our solar system had wonderful components in them, but they weren't special. They weren't rare. They were actually extremely abundant in the universe. The planets in our solar system have a reasonably unusual configuration, but the planets themselves, they're not rare at all. We know of thousands of planets like them. And so the sun is not special. Our planets aren't special. Our origin story is not special. So I think it is foolish to believe that life is special on Earth. I think life is inevitable because any theory that starts and ends with the exceptionalism of us is likely to be wrong, or at least mathematically implausible. So life is resilient. Life is great at finding opportunities. And so I think life is common. But whether intelligent life is common, there I have very little hope. There's only us, barely so, and for a blink of an eye.
Nova Now Universe Revealed is a production of GBH and PRX. It's produced by Terrence Bernardo, Jenny Cataldo, Ari Daniel, Caitlin Falds, and Jocelyn Gonzalez. Julia Court and Chris Schmidt are the co-executive producers of Nova. Suki Bennett is senior digital editor. Christina Monin is associate researcher. Robin Kazmer is science editor. Robert Boyd is digital associate producer, Shyla Duff is digital video intern, and Devin Maverick Robbins is managing producer of podcasts at GBH. I'm Alok Patel. We'll be back next week for, get this, a journey where we travel into a black hole. If you want to learn more about the science behind the universe, visit pbs.org/Nova Now podcast. And check out Nova Universe Revealed, a 5-part film series about the same topics we're discussing here, like alien worlds. Visit pbs.org/Nova. This podcast has been made possible by the Gordon and Betty Moore Foundation.
GBH.